Um, so my name is Akshay. I'll be the session chair of this session. And today we have three very interesting talks. The first one is on execution time opacity for one clock parametric timed automata. And the talk will be given by Johan Axel. Johan.
Thank you. So this work is a collaboration with my colleagues Etienne André and Angel Lefaucheux. And before I dive into it, I will make a small recap on time automata and on the notion of opacity. So time automata is a real-time formalism. It is actually a finite automata that is extended with real variables that we call clocks. And those clocks represent the real-time aspects of the system. Clocks can be constraints either on location of the automata. Here you have a constraint that we call an invariant that says that some clock X must be smaller or equal to 1 time unit. And it can also be constraints on transition. So if you look at the transition here from L0 to L1, you have a constraint that says that there is some clock Y that must be greater than 1, greater or equal than 1, in order for this transition to be enabled. And clocks can also be reset. So how does the system progress? So the state of the system is the location in which we are and evaluation for each of the clocks. And how do we go from one state to another? We have two possible ways of moving. The first one is to let some time pass. So we stay in the location, we let the time pass. That means all the clocks will be increased uniformly. And the other possibility is to perform a transition if there is some transition that is enabled. Now, the issue is that, is there an issue? It's fine. So since we are working with real time, well, clocks can take any real number, and that means that we have an infinite number of possible clock valuation. So what is used to represent the state space of a time automaton is a symbolic semantic, where a state will actually not describe one possible set of valuation for the clock, but so in the concrete semantic, we have only one possible valuation for in each clock. And so what we want is to have a set of constraints over all the clocks. And that's what we call a clock zone. So if you look at this example here, you have the start of its state space. And in the initial symbolic state, we can see that we have our two clocks, X and Y. They are equal to each other. And they are less or equal than 1. And this is because we have an invariant here. So this actually represents an infinity of possible clock value, actually all the real value between 0 and 1. So thanks to that symbolic semantic, we are able to have state space that are not infinite. And that's how we can do things with time automata. So that was for the first notion. And now the notion of opacity. So opacity is a security property. And in general, the idea is that if you have a system with some information that are private and some information that are public, you say that the system is opaque if by having the knowledge of public information, by having public knowledge, you cannot deduce the private information. So the private information cannot be deduced from public information. Now, in the context of time, what we have is something called execution time opacity, which is exactly that. It's opacity, but only when we consider execution time. So there is an example with the time automata. So we have the time automata here, and we have some location that we call private. And the idea here is that what we want for the system to be opaque is to not be able to know if we went through that private location. So the idea is that here we go from the initial location to some final location. And if we can reach this location on a run that doesn't go through the private location, we call this run a public run. And if it actually goes through the private location, we call it a private run. And so we say that the automata is execution time opaque for some time execution, from some execution time, sorry, if there exists both a private and a public run with that execution time. So let me give you an example. If I take execution time 2, then the system is execution time opaque for 2. Why? Because with this execution time, you cannot deduce whether you went directly to the final location or you went through the private one. On the other hand, if I give execution time, let's say 3.5, then it is not opaque because you know that it is not possible in this example for a public run to have an execution time of 3.5 when you reach the final location, because the invariant here forces us to leave this location at maximum 3 time units. So now that we have this notion of execution time opacity,
less than 1.
If we have, let's say, 0.5, yeah. So per our definition, it is not opaque. Also, it's interesting because there is, in this case, you can, if it's less than 0.5, you know that it's not a private run. And so here you can deduce that it's a public run. So now there is, I'm not going to talk about it here, but there is a notion of weak opacity that is only, so a system is weakly opaque. For instance, if you can deduce that you are not in a private run, but as long as you cannot deduce that you are in a private run, it's okay. So, okay, let's continue. So, so we have this notion of execution time opacity, and from this notion, we got 2 problems that are interesting. The first one is what we call execution time opacity, and it asks. So there are both decision problem. So the first one, the exists opacity one, is there at least one execution time such that the system is opaque for that execution time? And the other problem is the full execution time opacity, which asks, is the system opaque for all possible execution time? So those 2 problems on time automata were proved to be decidable. And so that's the state of art on time automata about that. Now that I have introduced this notion, I will get to the context on which we have worked, which is parametric time automata. So parametric time automata is an extension of time automata where clocks can now be constrained not only by given constants, but also by unknown constants that we call parameters. So the idea here, you have a new invariant in the example with some parameter p. So this parameter can take any integer value. What that means is that one PTA actually corresponds to a set of TA, a set of time automata. And if the parameter is not bounded, it's an infinite set. So we have way more expressivity, but at the same time, things are getting much more difficult because in this context, most problems become undecidable. So an example of the most studied problem in PTA is the reachability synthesis, which asks to compute, it's a problem where you want to compute all parameter valuation, so the value for P in this example, such that there exists a path to a given location. So a location is reachable for what parameter valuation is basically the reachability synthesis. And this is not computable in general. And in fact, the emptiness of the set of parameter evaluation is not even decidable. And so what we took an interest in is take the problems of execution time opacity from the time automata and try to apply them to parametric time automata and see what we could do with that. Was there something that was decidable about it? So from the two problems that I showed previously, the exist execution time opacity and full execution time opacity, we now get two variants. The first, that we call the emptiness, is a decision problem, which asks, is there a parameter evaluation such that the model is either exists ET opaque or full ET opaque? And the synthesis counterpart of the problem, which is a harder problem, asks to synthesize the entire set of parameter evaluation such that the opacity is verified. And so those problems are known to be undecidable. And that's where we started. And so we know it's not decidable. So the emptiness is not decidable and the synthesis not computable in general. And so the first step for us was to, the first step for us was to try to provide some algorithm for these problems, which is a method that will not always terminate, but when it terminates, it is correct. And so that's our first contribution. And this contribution is based on the notion of parametric execution time, which is quite close to reachability synthesis. So the idea is that we want to synthesize the set of parameter evaluation that allows to reach some location, but also the set of execution time, so the total elapsed time in the run, that reaches this location.
Sorry, so this parametric execution time, must it be an integer?
The parameters are integer
But not the execution time, right?
Oh no, the execution time, no. The execution time, it's real time.
Right.
Yes. Parameter are the constraints on the clocks, but the clocks themselves, we are always in dance time. Yes. So yeah. So the parametric execution time, you have an example here for our previous example. What the parametric execution time looks like. So it's a set of constraints over the parameters and the execution time, which are noted with D here. And the thing is, this notion is actually equivalent to doing a reachability synthesis of the automata when enriching it with a clock and a parameter that will actually keep track of the total elapsed time. And so reachability synthesis is something for which we already add some algorithm. So we can, thanks to this reachability synthesis, compute, when it's possible, the parametric execution time of an automaton. So how does that help us? Well, it so happens that there is a relation between the parametric execution time of public run and private run and our synthesis problem. So first, a note is that from parametric time automata, it is easy to syntactically restrict it so that we separate the public run and the private run. And so we can have the parametric execution time of both. And so how do we get the synthesis from there? Well, in the case of exist execution time opacity synthesis, it's quite simple. It's simply the intersection of both those parametric execution time. And in the case of the full execution time opacity synthesis, where we want only parameter evaluation where for all execution time, we have a run in the public part and a run in the private part. The trick is to actually take the intersection, but remove from the intersection all parameter valuations that appears outside of it. So what we do is we do the difference between the two parametric execution time, and we project parameters of this, and we remove this parameter from the intersection. So thanks to that, we have an algorithm that might not always terminate, but at least if it does, it gives a correct result. And what about the computability of this algorithm? So we know that what I just showed depends on parametric execution time, that itself is equivalent to reachability with +1 clock. And we actually know about reachability synthesis. And what we know is that it depends on the number of clocks. So in general, with 1 clock, it's computable. With 3 or more clock, we know that it's not. And with 2 clock, it's still open. It's an open question about whether it's computable or not with 2 clocks. The issue here is that since we need to add 1 clock, even in the simplest case, which is 1 clock and 1 parameter only, we are already in the unknown. So we don't even have a guarantee of termination for this algorithm, even in the most restricted class. So that's not very good. And our intuition was that in this context, 1 clock, 1 parameter, we should at least be able to have some computability. And so we try to see, are our emptiness problems decidable on 1 clock PTA? So PTA with only 1 clock. And the first issue is here that even when we only have 1 clock, the parametric execution time can still be infinite. So here you have an example. You have an example with 1 clock and 2 parameters, P and Q. And this here actually gives a parametric execution time that is infinite. That is a set of constraints of a parameter that is infinite. And so what we wanted to do, our first step, was to produce a method that allows to encode infinite pets on 1 clock PTA with guarantee of termination. So how we do it is a kind of divide and conquer method, where the idea is that if we have only 1 clock and it's never reset, which we call reset free, then the parametric execution time is computable, because if the clock is not reset, you don't need to add another clock to get the global execution time, because you already have it in the clock that's here. So what we will do is that we will decompose our automata in subparts without reset. And we will compute the parametric execution time of each of those parts independently. And then later on, we will combine them to create the parametric execution time of the global thing. So here is an example with a run with, yes? Sorry, can you repeat it?
The P2, is it for the parts or for the whole time automation?
So what we will do, what we want is to compute the pet of the entire parametric time automata. And what we will do is decompose our automata in little parts, and we will compute the parametric execution time on each of those little parts. And I will show you how you can actually combine them to get the parametric execution time of the whole thing.
So what does it mean to have P2 for the whole thing? You need one expression that...
Yes, we want a way to express this parametric execution time, even though we know that it is an infinite set of constraints.
Oh, okay.
So here is an example with a run with 2 resets. We will have, because we have 2 resets, we will decompose this run in 3 runs that will each be part of one of our little reset-free automaton. So how do we do that? For each couple of location, we create a reset-free PTA, such that in this PTA, we have all the run from one location to the other, such that the clock is reset only once when entering the location where we are going to. And actually, there is also another kind of runs that we keep, is if it's never reset, but it reaches the final location of the global PTA, which is the case here, the end of the run. So in this small example, we get two sub-automaton. The first one, L0, L0, represents this loop. And the second one represents going from L0 to L1. And in the following slide, the pets of each of the sub-automaton are noted with a Z, because it's a parametric zone that we are going to manipulate in order to get what we want, which is the parametric execution time of the entire automaton. So how do we recombine those zones? Well, we create what we call an automaton of the zone, which is a finite automaton, so it's untimed, and it's built on the location of the same location as our PTA. And in this automaton of the zone, each transition will correspond to one of our reset-free PTA. And we label this transition with the zone that we actually computed. And what we claim is that the language of this finite automaton is actually a representation of execution time and parameter valuation that goes for all the runs, that goes from our initial to our final location. And why do we claim that? How do we obtain the parametric execution times that we are looking for? Well, actually, since the automaton of the zone is a finite automaton, we can compute a regular expression. And so the alphabet of this regular expression is the zone that we computed. And now what we can do is actually replace the operators of the regular expression with some operation of the zone. And so typically what we do is the plus is a disjunction between two zones. The concatenation is the addition of execution time, because it means you've done a part of the run and then the other part. So you want to additionate the two execution time of the sub-runs. And you want to intersect the parameter constraint, since you want them to be true on each of the zones that you concatenate. And finally, we have the clean star, which is where we will get the infinity. And it is an infinite disjunction of the zone concatenated to itself as many times as we want.
What is that to the zero going to correspond to?
Yeah, so that's a good question. So this, I must show here. So this 0 means that, so the clean star corresponds to a loop. I will actually just go back for the sake of this. So this actually would be, the language of this would be, so ZL00 star concatenated to ZL0L1. So a star means that you loop some location. Yeah, but I need to, I needed to say that to make it clear. So because you take the loop as many times as you want, you can also take it 0 times. And so Z0 would be the equivalent of epsilon in what we do. And so since you have the question, I will tell you what it is actually. So it's a zone where you have no constraint on the parameter and the clock is equal to 0. And so if you concatenate this Z0 to some zones, you still get the zone. So it's a neutral element. For the previous example, I'm going to show it just next slide. Yeah, and so this regular expression is actually equivalent to the parametric execution time of the whole automaton. And here is the complete example. So we had two sub-parts, two sub-automaton, reset-free PTAs. We have the automaton of the zone, and we get the following regular expression. And if we develop the operators as I showed, we obtain an infinite disjunction of constraint that is actually the pet of our entire automaton. So that's how we are able to, from one clock PTA, compute with guarantee of termination the parametric execution time. So does that mean that we have won? Does that mean that we have showed that with one clock PTA, our opacity problems are decidable? No, not yet, because with the algorithm I showed earlier, you need to make set operations with the parametric execution time, and you cannot make this operation easily with infinite sets. You need specific arithmetic for that. So what we did is that we looked towards Presburger arithmetic, which is an arithmetic that allows to manipulate semilinear sets, which are finite union of linear sets. And so semilinear sets themselves were not able to help us because we cannot represent the parametric aspects in them. But what my colleague Angel Lefaucheux did is introduce a parametric version of Presburger arithmetic, which allows to manipulate some parametric semilinear sets. And the problem he took an interest in is what he called the parametric semilinear set equality problem, which is a decision problem that says, given two parametric semilinear sets, is there a parameter valuation such that the sets are equal? And what he showed is that, in general, this problem is undecidable if we have more than a certain number of parameters. And on the other hand, if we have one parameter only, then the problem is decidable, and the set of valuation that achieves equality can be computed. So how is that? Sorry?
Parametric semilinear set. How do you
Your question is what is a
describe the semilinear set?
So your question is what is a parametric semilinear set? A parametric semilinear set is a semilinear set, which is, so a semilinear set is a finite union, so it's a disjunction of linear sets, which are basically what can they express is typically, let's say you have, let's say the set of, I don't know, all the
semilinear set, parametric semilinear set.
Maybe I will finish and get back to
Sure,
that.
sure.
Yeah, okay. So the thing is, what I'm showing right now about this this parametric Presburger version, these results were done in another work by Angel Lefaucheux, and this is results that we will use in our work on parametric time automata to show some decidability results, or in this case also undecidability results. So how does this equality, this parametric semilinear equality problem relates to our opacity problems? Well, it so happens that it is quite close to one of our problems, which is the full the full ET opacity emptiness, which can be expressed as, if we take the parametric execution time of public run and of private run, is there a parameter valuation such that those parametric execution time are equal? So as you can see, it's looking quite the same. And what we were able to prove, is that the parametric semilinear set equality actually reduces to the full execution time opacity emptiness of one clock PTA. So we have the reduction on that side. And on the other side, for the case of one parameter only, we showed that our problem of full execution time opacity emptiness on one clock PTA actually reduces to parametric semilinear set equality. And thanks to that, what that means is that the full opacity emptiness of one clock PTA, we know that it is undecidable with more than a certain number of parameters, since we know that it's as hard as the parametric semilinear set equality. And what we know also is that if we have only one parameter and one clock, then the full execution time opacity emptiness is decidable, and the synthesis can be computed. So I will wrap it up with our contributions. We have some technical contribution, which is a semi-algorithm for the synthesis part of our problems. We have the encoding of infinite PET on one clock PTA with guarantee of termination. And we have also a translation from infinite parametric execution time of one parameter, one clock PTA to parametric semilinear set. And that is part of the proof that shows that our opacity problem on one parameter, one clock reduces to the parametric semilinear equality. And so on the theoretical side, what we have proven is that if we have only one clock and one parameter, then the full execution time opacity emptiness is decidable and its synthesis is computable. If we have more than a certain given number of parameters, then we know that it is not decidable and the synthesis is not computable. And what we don't know if we have between 2 and m parameters, then is it decidable or not? We don't know. And something else that we don't know, but that we might investigate in the future, is that with 2 clocks, so in the general case, we know that 2 clock is not decidable, but what if we have only one parameter? So one parameter and more clocks, is it decidable or not? And that is something we don't know yet. Thank you.
We have time for a quick question. Yeah, but I want to not break the, and then we'll come to your AAA question. Not to worry. Yeah. Are there any questions? If not, we'll move to the AAA question.
Difficulty in handling 2 clocks, extending your argument to 2 clocks.
Can you repeat the
So what is the difficulty in extending the argument of clock to 2 clocks?
To prove this matter to 2 clock one parameter. It's probably quite difficult. So first of all, this the way we proved things on one clock, so is based on the parametric semilinear sets, and that will only work with one clock. We can't express 2 clocks with them. We cannot reuse that. And what I must tell you is that so the reachability synthesis problem, which is a priori easier than our opacity problems, is still there is still no decidability result for 2 clocks, and it has been a long time since it's like that. So it seems like a question that's quite hard to answer.
It is known to be undecidable.
Yeah. So we know that in general, with 2 clocks or more, it will not be decidable. But the question is, if we have only one parameter, can we do things about that? And we don't know yet.
The question is 1 parameter, but 3 clocks, what happens?
Okay. Well, as now, with one parameter, if we restrict to one parameter and as many clocks as we want, we don't have proofs of anything. So I don't know.
Okay, thanks a lot. While the slide change is happening, maybe we can use the time to do some AAA question answer session. Would you like to interrogate the audience with some question? You'll have to give the mic. I have a question, but I thought I'll give him the opportunity.
No, please go ahead.
I think easy question. After that, he can give the tough one. What's the difference between excess ET opacity and full ET opacity? Oh, that is fast.
Okay, this CT opacity is the execution time D for which opacity, which means at the same time, and full opacity is execution times D, we have public rise.
All right. On that note, let's thank the speaker again. We are running a couple of minutes late, but let's start with the second talk of the session, which is on Myhill Road. We continue on the theme of time data meta, of course, in the session, and the second talk is on Myhill Road characterization of a time data meta, but this time with integer resets. And the talk will be given by Srivatsan.
Thank you, Akshay. Yeah, so this is a joint work with Kiveli, who is there in the audience, and Pierre Gonti. So this is about a Myhill-Nerode style characterization for timed automata with integer resets. Let me try looking at that. Okay, so this is the outline of the talk. So first I will recall what is the Myhill-Nerode theorem that we know from regular languages. Then I'll talk about what we want to do with it in the timed automata context and what are the challenges. And then I will talk about the results. Okay, so this is the Nerode equivalence. So we start with the finite alphabet sigma, and L is some language. And what is this Nerode equivalence? It's an equivalence on the set of all finite words. So two words are equivalent if, one second, how is the pointer? Okay. So two words are equivalent if their residuals are the same. So what is a residual of a word? That is given here. So for a word, its residual with respect to L is the set of all extensions that puts it inside L. Okay? So this is the standard Nerode equivalence. This equivalence has some nice properties. The very first thing is that it's sort of monotonic. So if I take two words in one class, and if I attach the same letter to both of them, they will also be equivalent. Okay, so this is the property of monotonicity. The second nice property that it has is that the language L can be obtained as a union of these equivalence classes. There will be no class where one word is in the language and is not in the language. Okay, so this gives a very nice picture because it can immediately be constructed to an automaton, where you look at all these bubbles as states, and then you can put a transition between states. From U, you have to just go to the state, to the class where UA is present. Okay, so this gives a very natural way of going from equivalence to automata and also back. So if I take some automaton, let's take a DFA, we can derive a monotonic L preserving equivalence as follows. So given the automaton, we say that two words are equivalent if both of them go to the same state. Okay? Sorry. Yeah.
Just wanted to the minimal automaton.
No, any automaton. Yeah, right. Okay, fine. Okay, so yes. So the point is any automaton gives rise to an equivalence. So essentially the point is you can think of automata as equivalences, equivalences automata. So you can try to interchangeably think about them. Okay. And now coming to the Myhill-Nerode theorem. So this is completely on the equivalence side. What does it say? It says that let me take a language. L is regular if and only if the Nerode equivalence has a finite index. That is the statement of the theorem. Essentially, okay. And moreover, this equivalence is the coarsest among all the monotonic L preserving equivalences. Sorry, finitely many classes. Okay. Now, what is the implication of such a Myhill-Nerode theorem? It says that So this is what Akshay just pointed out. The automaton that you get from the Nerode equivalence is actually the minimal automaton, minimal DFA for this regular language. And also there are this Mayel-Nerode theorem also forms the basis for the Angloan style learning algorithm. Fine. So what is our goal? So we would like such a Mayel-Nerode characterization for some timed languages. Okay, so we saw what timed automata are. So I will shortly recall, and our aim is sort of twofold. We want to first of all get a Mayel-Nerode characterization, and then we also want to apply it to timed automata learning. So that is the first part of the talk. So now let's get into timed languages and timed automata. So what are timed languages? So let's start with timed words. A timed word is a usual word, but it is decorated with some real numbers, which are delays. Okay, so there's one difference if you are used to a normal thing, which is the delay here denotes the time between the previous and the current event. It's not a time stamp. Okay, it's the delay. Okay, and a timed language is a set of timed words. So here is, I'm not going to do everything because it was there in the previous talk. So let's look at an example of a timed automaton. So if you see, look at this language. It's a set of all words of this form, D1A, D2A, sort of D and A, such that the sum of the delays comes to 1. And we need an automaton to recognize this. And how do we do that? So you're in an initial state, you keep reading your A until the clock, which is accumulating the delays seen so far, is still less than 1. And the moment the value of the clock becomes equal to 1, you make this transition, right? And still you may see words with 0 delays after this. And so as long as the value of the clock is 1, you keep accepting. Okay, fine. Here is another example which shows another operation. So look at this language. It's a set of all words where every delay equals 1. Okay, and here is a very simple automaton for it. You just check if the value of the clock is 1 and then set it to 0. So the next time when it reads a letter, it will check if it is 1 and it will set it to 0, and so on and so forth. Fine. So here is our goal. Once again, Mayel-Nerode characterization for subclasses. Now, what are the challenges in this problem? So the very first challenge, if you want to lift the Nerode equivalence as it is to the setting of timed words, it will be infinite. So here is the example. Look at this same language. And suppose I take this word where the delay is D1 followed by A. What is the residual of this word? It is a set of all words such that the sum of these delays is 1 minus D1. Right? These are the extensions which are going to be putting me into the language. But for each D1, there will be a residual. Right? So the number of residuals is infinite. Okay? So we cannot hope to just work with this. Here is another challenge. It's just not the fact that the residuals are infinite. Even if two timed words have the same residuals, they may not go to the same, sorry.
Is there a loop in the?
No. So suppose I see a word, let's say 1A, 0A. Okay?
Oh, I think.
Yeah. Okay. So the second challenge is the fact that if I look at, there are examples where I have two words which have the same residuals, but they can never go to the same state in a timed automaton. So I will show you what it means. So look at this example. So what does this say? It's a simple thing. You just read A followed by B. But if the first A comes between 0 and 1, then the B should come at 1. If the first A comes between 1 and 2, the B should come at 2. Okay? Now let's take two words, U and V. So U is 0.5A. The residual of this with respect to this language is 0.5B. That is the only possibility. Now, what about V? It is 1.5A. Residual is with respect to a certain language. No, I'm saying there's a singleton word. No, which you are talking about, which this example or? Yeah, right. So there's only one way to complete this in order to go to Q3. You see, like suppose I'm 0.5a. I will be here. And when I do B, I need my X to be 1. So my X is already 0.5. And for it to take this, it can elapse 0.5 more time units. And that is the only possibility. For instance, if this was X bigger than 1, then there are many more possibilities. Anything bigger than 0.5 was. Okay. Now, similarly, if I look at V, it's 1.5a, and the only possible completion is 0.5b. Once again, the residual is the same. But we can argue that these two words can never go to the same state in any automaton. See, in some sense, after reading this letter, I need to check for x equal to 2. Okay. And similarly, after reading this, I need to check for x equal to 1. Okay, there are no other options. This is a very hand-wavy sort of an argument, but one can, I mean, I don't have time to do the proof of the fact that no, they cannot go to the same state in any timed automaton. Good. And finally, the third challenge is the fact that, so previously when we had equivalences, we were able to just simply convert them into automata, and from automata, we were simply able to convert them into equivalences. So we need an equivalence on timed words, which is amenable to such an automata and back and forth sort of a conversion. Fine. So now I'll talk about some existing work in this related to this. So the first work that I would like to point out is Swavik's and Mikoai's work on. They have come up with a certain Myhill-Nerode style characterization for deterministic timed languages. So they extended the model and they used a notion of orbit finiteness to achieve a Myhill-Nerode characterization. That is a summary of it. And another work is by Mahler and Pnueli, where they look at the notion of recognizability, where the existence of right morphisms onto subsets of the set of timed words. They kept the idea of learning in mind, and indeed in last year, these ideas got translated into a learning algorithm for deterministic timed automata. So one point is that it doesn't guarantee any sort of minimality. Okay. And here is another work which looks at, instead of an extension of timed automata, it looks at a subclass of real-time languages. These are languages obtained by one clock timed automata, where that one clock is reset in every transition. So essentially, you can check the time between consecutive events. And if you look at these kind of languages, they have a learning algorithm and a Myhill-Nerode relation. How am I doing with time? Yeah. 10 minutes over. Yeah. Okay. So, and then the other thing is there is this subclass called event recording automata, where you assume that there is a clock associated with every event. And in this case, this is, to my knowledge, the first subclass that for which learning algorithm was considered. And recently, Anirban, who is an author of this work, is in the audience. So they extended this with a better algorithm, so which they call gray box learning. Fine. So there are many more works, more on learning one clock timed automata. So here is a summary. So there are several works on learning methods. So little less limited literature on Myhill-Nerode, except for the work by Slavik. And here comes once again our goal. We want to establish this kind of a Myhill-Nerode relation for the subclass called integer reset timed automata. Okay, I will explain what that is. So what are integer reset timed automata? So here is the syntactic restriction. Whenever I reset a clock, I have to make sure that there is a guard of this form. It has to check that some clock is equal to a constant. Now, what is the implication? So I start with 0, right? All clocks are 0. The first time I reset a clock, it will check that some guard is an integer. So which means the point where I reset the clock is an integer. I mean, the time, as in the time elapsed so far, is an integer. Once again, the next time I reset some clock, I look at the time since the last I reset, and since then only an integral time should have elapsed. So what this implies is that all the starting points of your time constraints are at integral timestamps. Okay? So this is a model, this is an Indian model, Vijay Suman, Krishna, Paritosh, so on. So their motivation came from some automotive examples. They figured out that actually what the model was doing was it was actually doing an integer reset. Okay, but then it was very attractive for a theoretical study. Here are very nice properties of this. So every IRTA can be converted to, sorry, yeah.
Since all integers, then it's effectively an integer reset. Oh, okay, who will you?
Whenever you reset, you check for an equality.
No, I mean, generally in a time
Yeah,
also you can assume.
yes, yeah, you can have like, yeah, that's right. So it will not,
But
if you have x less than 1, I can reset.
Yeah.
So long as maybe for exit right? Because on the reset.
Oh, okay.
Yeah. So every IRTA can be converted to a one clock deterministic IRTA. So that's the point. So having multiple clocks is not necessary here. And what is the idea? Because you look at any configuration, all the fractional values will be the same. Because they were all reset at integer points. So you can, all fractional values will be the same. And so you can keep the integral values in the state and use the one clock for maintaining the fractional value. That is roughly the idea. Okay. Come again?
How do you know the maximum integral value to keep in the state?
It will be the same constant. I mean, it will come from the max constant.
Assuming that you know the rest.
No, yeah, I start with an automaton and then I can convert it to an IRTA with one clock using the same max constant. I keep only all the integers up to the max constant, all the tuples. Okay. Fine. So there is even better, there is something called a strict one IRTA, which is the final thing which we will be using anyway. So, which is that, so right now we have reduced it to one clock. And we said that you can reset only when there is a transition of the form x equal to c in your guard. But here is a stricter version. Whenever you check for an x equal to c, you have to reset it. Okay. And with this strict version, I mean, you can also convert any IRTA to a strict IRT. Okay. So that is the that is where we are. Now let me start with the results. Okay. I want, these are the set of all timed words, and I want an equivalence that is monotonic. I do not know what this monotonicity is yet, so that I can derive it, I mean, I can convert it into some class of IRTA. Here I would like a strict IRTA. Okay. So to that, here is one technical object that we will use, which is, suppose I have a constant k. Okay. And to every word, timed word u, I'm going to associate a number as follows. So let's say the word is D1 something, D2 something. These are all the delays. I start from the left. I look at the first point when the sum of the delays is an integer which is less than or equal to k. The idea is that an automaton which reads this letter would check for a guard of the form x equal to c with c less than or equal to k, and it would have reset the clock. Okay. So at this point, I stop the computation and I again restart my counting from D3. Okay. I look at the next point where the sum between the consecutive points that I've chosen is again an integer less than or equal to k. And once again, I stop it. And then I do again and so on. Okay. Let me give you an example. So for instance, if k is 1 and this is a timed word, I start from the left, 0.2, 0.8. 0.2 plus 0.8 is 1. I stop. That is the first point. Then I'm left with 0.2. So that is C1 of u. Here it is 1.2, 0.8. It's already bigger than 1. So I don't do anything to it. And 0.2, so it is 2.2 here. Okay. So the nice thing about this number is that as soon as I give you a word, no matter whatever strict IRTA you run it on, the value of the clock in the end will be the CKU. It's input determined. It's not automaton determined. Okay. And this is a very, very helpful aspect. Okay. So this is what we will use in defining our Myhill-Nerode equivalence, Nerode equivalence. Okay, and before that, what I need to define what is a monotonic equivalence here. Okay, this is the so U and V are timed words. 5 minutes. I'm done. Yeah, U and V are timed words. The first thing that I impose is that this object should be more or less the same for both words. If you know what region equivalence is, essentially it should be in the same equivalence class with respect to K. It should be in the same interval up to K. Okay. And secondly, if you remember that example, there was a 0.5 and a 1.5. With respect to 2, both of them have different CKs. Okay. And so they will be put in different classes in some sense. Okay. Even though their residuals were the same. Now, the second thing is the monotonicity. Suppose 2 words have the same CK. Now, when they elapse time and hit the same CK values, okay, then they should, whatever letter you read, they should be made equivalent. So here is what it says. Suppose U is equivalent to V, okay? And in addition, I know that CKU plus D and CKV plus D prime are equivalent. Suppose I pick D and D prime of that kind. Then the successor after delay D and D prime should be equivalent. If you don't understand the entire thing, it's okay. It's essentially a counterpart of monotonicity from the untimed world. Okay. And with this definition of monotonicity, we get what we want. Okay. If I take any K monotonic L preserving equivalence, I can convert it into an IRTA with a special form in which for every state I can also associate a region. Okay. We call it a K acceptor. So whenever you come to this state, the values will be in certain interval, either 1 to 2 or 2 to 3 and so on, or K to infinity. Similarly, if I take a K acceptor, I can define a similar monotonic equivalence, L preserving equivalence from it. So this is what we wanted and we achieved it. I mean, partly in the sense we wanted monotonic L preserving equivalence in the time setting, and we have given a definition of monotonicity. Fine. What we are left with is the Myhill-Nerode theorem. Okay. So here is the last part. So if I take a time language, here is the equivalence that I'm going to define. I say that U is equivalent to V if first of all these 2 objects are equivalent, and moreover the residuals are the same modulo a rescaling function. So because I cannot just say U inverse L equal to V inverse L because there are infinitely many, but I can do some sort of rescaling, and I will not give the details of this rescaling. And this is the final Myhill-Nerode, this is the Nerode equivalence. And we get a theorem which looks like this. If I have a time language, I can say that it is definable using an IRTA with a constant K, if and only if this Nerode equivalence is K monotonic and has finite index. So previously we just had that finite index in the untimed case, but in the timed case, we cannot just assume monotonicity. If it is monotonic, then it is okay. Okay. And finally, this turns out to be coarser than any monotonic L preserving equivalence, similar to the untimed case. So how many, do I have 3 minutes? Good. Okay. So here is one quick example. So you can use this to say that some language is not IRTA definable. So for instance, if I look at the set of all words of this form, x dot a, such that x is any natural number. Okay, so there is no bound on this, and we cannot use a timed automaton to recognize this. And by running through a sequence of steps, you can figure out that for no k, this equivalence is monotonic. So this gives us a way to show that some language is not IRTA definable. That's the point of flashing this slide. Okay. Similarly for an example. And so what are the consequences? We get a canonical K acceptor for a time language which is recognizable by an IRTA. Okay. And this also leads to a learning algorithm whose details are in the paper. The main idea is this. See, the goal is to identify the classes of this equivalence. I assume that K is known to me. Okay. The goal is to identify the equivalence classes of this relation. It turns out that for every class, there is a half integral word that can be a candidate in it. What is a half integral word? The delays are from this set. There are not any arbitrary fractional delays. Okay. So using this, we develop a yeah, it's the same as k plus 1 actually. So yeah, okay. Yes, that's about it. So here we have a Myhill-Nerode theorem and it leads to a canonical form. It can be computed using a similar minimization algorithm like in the DFA case. All identical algorithm, and there is a canonical form that we can learn almost identical to the L star algorithm for DFAs. And in future, we are trying to see how this relates to the learning methods that have been implemented in the literature. Does it give any gain and what to do for that purpose? Thank you.
So some questions, yes.
So in the timed automata literature, it's always been delays, as you pointed out. A lot of applications actually want cumulative clock readings. Would there be any real difference in the integral, if you do these strong integral resets? Would they, I mean, you can reset the clock, that's fine.
Okay.
But it's reset at an integral point. Would there be any real difference in taking that inverse operation and so on?
Yeah, so there is a real difference. So I'm sorry. Yeah, you see, that's the actual problem. We tried investigating it when it is not an integer reset. We have some preliminary ideas and so, but it's much more complicated because here you have certain points where you know that the clock will get reset and so on. Yeah.
Cumulative clock reading. But you don't have the delay based time.
But you have like the normal time word.
No, it will be the same. It will it's just more convenient to technically, yeah. Yeah, it's the same, yeah.
Actually, but I have the other question, which is where does this proof fail when where all that's
Yeah, where all is
when you move?
So first of all, we don't have a counterpart of Ck of u, which is the input determinacy. I give a u, if I know Ck of u, whatever my automaton is, by the end of reading this word, the value of would be Ck of u. But yeah, I don't have in general. Okay. This is what we need to work on.
Other classes where you don't know this input determinacy, it reminds me of other places where like even clocks and so on, where you know a bit more.
In event clocks, it is input determined because I look at the.
I think there is this work also on input determined, which even extends in clocks, right? So it's
Yeah, yes. So see, for the other subclass with real time where you reset everywhere, that is also kind of easily input determined. Okay, somehow we need a reasonable class, which is from where if I read the word, I know this is what the value of the clock would be. Roughly, that's the.
so for even clock automata, you think you can get such a, because here I guess the consequence of this is that you are getting a minimal
Yes.
IRDTA, right? Given a language, you are able to get a minimal automaton.
Yeah.
Which I don't know how to do even for event clock automata.
No. For event clock, there is some work which the learning work, but they look at what is called symbolic words.
Yeah.
Yeah. That's that's a different thing. I don't know what. Yeah.
Okay. Any other questions? Yeah.
So this alternative is normal in terms of number of sets.
Yes.
But let's say the number of resets or constants used.
Constant is this. Okay. Well, it's the same constant. Okay. And whenever I have a guard.
Same meaning what?
So see, I can give you a timed automaton, let's say a normal IRTA, you can use as many clocks as you want. You can be free with your resets. Suppose I give you a timed automaton of that. I can convert it into a canonical acceptor with this blow up, which is written here.
About canonical and what?
Among all the K acceptors. You see, like we have to talk about canonicity under this class of automaton.
In terms of the actual IRTA I get. Like what can I say about its minimality?
This is, you mean, okay. So the question is, can I work with a smaller constant and probably get a smaller, this is, it's not clear actually. So how to the constants are not clear. Okay. Once we fix a constant, we know what to do. Across constants, what is better, we don't know.
Maybe while Felix is setting up for the third talk, we can have the AAA session question. I first want to give Srivatsan the chance to interrogate back. Is there something you want to ask? Will it be easy or difficult? Tough, tough, super tough.
What is the Mile-Nerode relation? I'm sorry.
Yeah, this is not fair. Even without attending your talk, they cannot answer. I'll give a question. What was the first reference that he pointed out?
Okay, maybe I have a question actually. So I showed you an example. You don't have to answer it immediately, but I showed you an example which had a challenge. Oh, excellent. I mean, so we don't need to ask any more. Okay, no. So the question is, so I showed a challenge, right? I mean, the challenge was there are words which have the same residuals, but they never go to the same state in any automaton. How did we address the challenge in our final relation? I'm sorry. I mean, think about it and you can tell the answer later. So
Aishwarya has lifted hand. We'll do that later. Okay. Because we don't have that much time, let's go ahead. Because I was going to ask how many references did he give? All right. Thanks, Srivatsan. So we'll move on to the third talk and the final talk of this session. The third talk continues on the spirit of timed automata, but this time we have counterfactual explanations for MITL violations. And this talk will be given by Felix Jan.
All right, thank you. Is the mic on? Yeah, excellent. All right, thank you. So last talk of today's opening day, but I have good news for you. I hope the last talk won't get too technical, won't get too proof heavy. I have maybe 1.5 definitions for you, and we'll talk about one theorem. But what we're going to focus more on is to think about what it means to have counterfactual executions of real-time systems, of real-time runs, because what we try to do is to find counterfactual explanations for MITL, which is a real-time language for MITL violations. This is joint work together with Ben Finkbeiner and Julian Sieber, and where we come from roughly is this model checking and verification direction, and I think this basic process is familiar to every one of you. Model checking takes a system S. For today, this will be our enterprise, and takes a specification, for instance, that the enterprise should successfully enter the warp drive, and then it tries to answer the question whether the system fulfills the specification. And okay, if this is the case, it returns a positive answer and everything is fine. And if this is not the case, what most model checkers do is that they can provide you a counterexample witnessing the violation of the specification. However, if we think about a large system as our enterprise, this counterfactual execution might get quite long. So this might be execution returned by the onboard computer of the enterprise. And the problem is that even if you can spot in this counterexample execution the point where the error occurred, it is not clear at all where the reason for this error is. So it might be in a completely different point of the program execution. So for instance, here that the warp failed might be due to the fact that early on we forgot to open the brake. And if you think about debugging or so, it's quite important to find the points where our system execution started to go wrong. So what we want to do is that we not only want to answer the question of model checking, namely, how do our systems behave, but we want to know why they do so. And this is the place where causality comes in, this notion of causality. So as a good researcher, I dive into causality by picking up a Wikipedia quote. But I think it gives quite a good intuition. It says causality is the influence by which one thing contributes to the production of another thing. So it's about the production of one thing to another. And the cause is then partly responsible for the effect, and the effect is partly dependent on the cause. And this idea of causality was of large philosophical relevance for a long, long time. Already over 2,000 years ago, Aristotle and others thought about this. Different families, different concepts developed. And one of this family is the family of counterfactual concepts. And the counterfactual thinking goes in a nutshell in the following way. If you think counterfactually, you imagine that if our first object, so which might be our cause, you imagine that this object had not been, and then you ask whether the second object would then also not have been occurred. So if this is the case, then you have this typical counterfactual reasoning thing stating that if the first object had not been, the second had never existed. And you see that this is also quite old. Back in the 18th century by David Hume, who had such counterfactual ideas, but it then became popular again, or it was popular all the time, but it became popular for the formal communities by the groundbreaking work of Halpern and Pearl starting in 2001, where they developed a formal notion of actual causality, which then allowed different formal fields, even to law, but also, of course, all the formal computer science areas to use this formalism of causality and to work in this direction. So what does Halpern and Pearl causality mean? Halpern and Pearl say informally, so this is now our half definition to say so, they say that a set of events, so they talk about events, is a cause for an effect if three criteria are fulfilled. So first, they require that the events as well as the effect did really occur. So it makes no sense to talk about causes that haven't occurred and also not to talk about causes for effects that haven't occurred at all. The second one is exactly this counterfactual criterion, where they ask whether in a counterfactual world, we talk about what this means in our setting later, in a counterfactual world in which our events, our set of events have not occurred, then whether the effect has also not occurred. And lastly, they require minimality. So they want their set of events to be minimal, stating that no smaller set satisfies the first two conditions. And there are well-known decidability results. If we have a finite range of events for finite alternative events, I think you can easily think by yourself that as long as we are finite, everything is quite clear and decidable. And as I mentioned, causality and then also this notion of actual causality is quite popular in computer science. Already in the 60s, there were works on so-called program slicing, where you try to analyze the dependencies in a program, the dependencies between different variables in a program, which you can consider to be kind of a causality notion. Then there was error localization, which we will do in some sense as well, which tried to reduce the produced counterexamples, for instance, of your model checkers to the essential parts that were responsible for the violation. And then, very important for us, there was the work of Hannah Chokla and others in 2012, who took the Halpern and Pearl causality, which was rather philosophical. They used structural causal models and applied it to the linear temporal logic setting to explain violations of linear temporal logic. This was then also developed further by Noreen Köhnen and others, who did it then for the hyperlogic of LTL. And all in all, to summarize this part of related work, I can really recommend the excellent written overview paper by Crystal Bayer and others, from verification to causality-based explications from 2021, which gives a great overview of this field of causality in verification. And what we try to do is now do all the thing in the setting of real-time systems and with real-time specifications. So I guess this is why I speak in this session. And yeah, try to find explanations for counterexamples of violations of real-time specifications. As I mentioned, we do it for metric interval temporal logic. It's not that important what it is. It's just so you don't need to know the details. It's just the real-time equivalent to LTL to say very roughly. All right. For introduction, I thought to go over real-time systems, but I think we had 2 talks doing this. So real-time systems have no discrete time steps, but varying real-time values, and they are commonly represented as timed automata. So here is our enterprise, very simplified model. So we have an initial state in which you can open the brake, then go further to open state. And then you have to wait 3 time units. So there's again our clock with assignments and with guards at the transitions. So you have to wait 3 time units until you can reach the warp state with an action energy. If you do this energy action earlier, you proceed to an error state. So it's crucial to satisfy those timing constraints. As mentioned in the talks earlier, you then have transitions guarded with clock expressions, with an action and with an assignment. And what we can then look at in those real-time systems in which the time is spent in locations are runs. You have an init location where 40 time units are spent, and then open breaks, 2 time units, and so on. So it's just a run in the system that can then also be transformed in the corresponding trace. Nothing spectacular happened there. So as mentioned, we want to find a notion of real-time causality in this setting. So we have our timed automaton. We have our effect, which is basically just a property on our runs, MITL formula. And we have our system runs of delays and actions. And now the question is, the first one, what events should we consider? And I think it makes a lot of sense to think about actions in our timed automaton as events. So if I open the brake, this is somehow an action. If I make energy, this is also some kind of actions, some kind of event. So we have this set of action events that are just our actions with a integer index saying at which position of the run this action was. But then we, of course, also have this crucial time behavior of real-time systems. And therefore, we also want to consider delay events. And this is now just our real-time value right there, again, with the position index. And we then want together consider those action events and the delay events, because, again, timing can be crucial in our real-time systems. And well, now the question is, can we go straight forward and just define Halpern and Pearl causality as a notion on this set of events, which is the union of our action events and our delay events? And if you think about the decidability results I presented, you run into a problem because our delay events induce infinitely many alternatives. And I think this is quite intuitive if you are known to real-time systems. We have here this real valued range. And if you think about, I have done a delay of 2, what are the alternatives? You run into infinitely many options. And so we have an infinite range, and it's not that straightforward to do. So let's solve this challenge. But first, yep. Sorry? And the run is fixed, yes. Yeah, so the run is fixed, and we look at the delays in this run with the position index. So this is basically delta 1 and then 1. No. Okay. So as mentioned, it's not that straightforward, and maybe this is also the reason why there is not that much work on causality in real time yet. There is work by Stefan Leuer and others from 2019 and Sorry?
So is the question that if you run from this that you run, will that?
Yeah, we come to this in a second.
Okay, okay.
I think it will become clear in a second. So there is work by Stefan Leuer who considered clock bounds and delay ranges, so more of a symbolic character. But what was indeed the gap is that there was no notion of real-time Halpern-Pearl-like causality that considers both actions and delays as causes and therefore as explanations for our system behavior. But let's try to come up with a definition for real-time causality anyways. So we have our timed automaton, we have our fixed run in this timed automaton, and its corresponding trace, not that important, and our effect psi. And now we want to define what it means for a set of events to be a cause for this effect in this run of the timed automaton. And now we call what Halpern and Pearl did. They had three conditions. And this is exactly what we'll do as well. We will also come up with three conditions. The first one, bit technical, sorry for the quantifiers, but basically says that the effect and the events did occur. So all the events occurred and also our effect occurred on the run. The third condition is straightforward as well. We don't want a strict subset of our set of events to satisfy the first two conditions. But the second condition will now get a little bit more harder, and I think this will then answer your question of those alternatives. So consider a trace of a run, and for now, let's think about the case where we have no causal events, so nothing is considered as causal. What we then want to do is to construct a so-called counterfactual trace automaton. And this counterfactual trace automaton should represent all the possible counterfactual and what you asked for, all the alternative events that could appear. But if we have no cause in our set of events, so no causal events, well, then we just have our trace. And how can we represent just this trace? Well, by using our timed automata again and fixing every delay to be as in the original trace, and by fixing every action to be as in the original trace. So what this does is just allows one trace, at least until this prefix, what happens later is not that important for now, to be exactly the trace above. And if we have now something in our set of events, for instance, an action, we relax our condition right there to allow not only our action alpha 1, but to allow the whole alphabet of actions. So now we have all possible actions right there, and then everything else is fixed again. Same what we do if we have causal delay events, we relax our guard condition right there. And of course, this can be combined to have actions and delays at different spots or also at the same spot. Just an automata theoretical construction. And what this indeed does is that it enforces all the non-causal events in our trace, and it allows alternatives for the causal events in our trace, and it allows all alternatives, and therefore indeed captures this infinite number of possible alternatives in a finite automaton representation exactly by using our timed automaton. All right. And with this, we can complete our definition by saying, well, we want in this counterfactual reasoning to have a counterfactual run in our counterfactual trace automaton. So it should be counterfactually. It should be also part of our originally given timed automaton because we wanted to respect the dynamics of our timed automaton. It shouldn't be, a train or so if we talk about the enterprise. And we want that our counterfactual run does not satisfy the effect, and therefore, indeed, our effect does not occur. So very similar, we had a counterfactual world in which the events did not occur, and then also the effect does not occur. All right.
So, sorry.
Yes.
Would it be existentially or universally quantified? Point two. Is it that for every run you or
it suffices to have one possible counterfactual run. So it's indeed an exists. Because we want that there is one alternative and not all and not everything. Yeah, exactly. Again, because we want that this counterfactual run does not fall from heaven and does anything, for instance, simulating a train or so, but we want that it respects the dynamics of our given system. So it should be possible to do this in our system. Yeah, so it's in the intersection because we don't want that.
Yeah. So if I have a time operating my system in which all happens are bad, right? Then I never have a counterfactual.
Yeah.
But that's not.
If-
And does that mean that there is no effect, no cause of this?
If all your runs are bad, then you don't find a cause. That's right. Yeah. If your program was that bad, we can find explanations. But yeah, you're right. Okay. So let's quickly check how this plays out. On our example, we have our enterprise, we have our effect. In this case, that an error occurred. We have a run the same as earlier, and now we want to ask whether the second delay of waiting just 2 time units is indeed a cause for our effect. And what we do is, well, we check all the conditions. Satisfiability is easy; it's satisfied, and then we go further to this counterfactual. This counterfactual trace automaton, we relax this condition, and then we indeed find a counterfactual run that waits 4 time units right there, and then indeed prevents the error but reaches the warp. So in this case, our counterfactual run is there, and we have the counterfactual condition satisfied, and also minimality is satisfied. All right. But this was one example, and now the question is, well, you can give me examples as you like, but is this a good definition? Is this a right definition? But going back to Joseph Halpern, he says something really, really interesting. He says in one of his talks, what's really hard about this area of causality, I'm going to give you a definition and would love to be able to prove a theorem that says this is the right definition. We saw it in the last talk, for instance. I'm a theoretician. That's what I do. I prove theorems. But I don't know what it means to have the right definition of causality. I don't know what the theorem should even say. So he don't know how to write down, this is a right definition of causality, and this is really a problem. What you can do instead is that he says, the way you show your definition is good is to show that, gee, look at how well it does it all in all the examples. And does it all in the examples, or does it good in the examples, means matching the intuition. You know, we have an intuition what should be a cause for something else. We have an intuition what should be an explanation. And this is in fact what we have to do in this field of causality, in this field of explanations. And this applies also to our area of real-time causality. And therefore, we also looked at really different notions. We looked, for instance, not only on the delay perspective, but also looked at absolute time steps. And more importantly, we also looked at progressively more refined notions of causality and therefore of explanations. For instance, I presented it to you for non-networks, but we did it in the paper for networks as well. And then also for the notion of actual causality, which was the notion developed further by Halpern and Pearl. Quick note on what this looks like. If we have, for instance, a network, it's just a simple mutual exclusion protocol, and we have a run in this network. Well, we can now say with this more refined notion of causality that violating this exclusion protocol is because of a delay in a certain automaton. So we are then automaton or component specific. And what actual causality does is that it addresses the problem of preemption by adding so-called contingencies. This gets then really technical. You have here some kind of a contingency automaton with a lot of edges coming in. The story is just, it addresses in these cases of preemption this problem to get more precise explanations. Yes. Really quick then on the algorithmic side. So here's our definition again. And I think it's clear that the first and the third condition are quite easy to check, while computational heavy for the third one. But what is about the second condition? And was the question. It's indeed about whether there is such a run and violating our effect. And this is then exactly how we can reduce our cause checking problem through the model checking problem. And by this, remark, we then get our mentioned first and only theorem stating that the cause checking problem is decidable and that we can then also compute causes by, for instance, enumerating all the actually happened events, and that both is X-base complete, which is then sorry? Sorry?
No, the cost checking
Yeah.
problem. You fix a C and ask whether it is.
It asks whether given an automaton and the effect and the run and a set of events, is this set of events a cause? Yeah. And computation is then computing sets of causes.
If there is a set of events.
I mean, whether there is a set of events is basically also, again, model checking problem, because if there is a trace not violating our specification, then we get an explanation. Yeah. All right. And with this result, we could implement a prototype tool. I want to emphasize its prototype. It's based on UPAR. We have here our enterprise warp drive in UPAR, and you can then, for instance, as a TXT file, enter a trace, but you also could enter a run, and then it's quite small, but you have to believe me that here it computes as an explanation, for instance, the second delay of 2 right there. Okay, so this is then for having an automatized explanations and automatized causality. But the problem, guess what? Scalability. So if you want to ask in the question section, does this scale? The answer is, well, not sure. So for cause checking, it's quite okay, I would say. I mean, we have this complexity of the model checking problem of real-time systems, but the real problem comes for the computation, because we have to enumerate, basically you can do it in a bit clever way, but we have to enumerate all the causes and then checking them. So this is quite hard, and therefore it scales really badly. And yeah, I mean, you have to check those causes, you have to do the model checking, you have to solve the model checking instances, so this takes time. Which brings us near to the end, because we want to improve on this, of course, and one idea is to not look at those concrete causes, those concrete events, but to do it in a symbolic way by looking at sets of events, sets of traces that could cause, that could have been a cause. And then if you do it symbolically, you then get, for instance, something that says, well, our effect is caused by a property also expressed in our language. There is work done on symbolic causality in discrete time. It might be an idea to extend this to real time. Of course, a natural point of further work is the tool development. I think we can do things on runtime. UPAR only has a fragment of MITL, so maybe we might switch to another model checker to get full MITL explanations. And this is not a really cool visualization of our explanations, so this might be a point as well. And then lastly, it might be also interesting to think more about those representations of counterfactual and explanations in an automata theoretical way, maybe also in other settings, or maybe this computer scientific, this real-time, this automata perspective helps also in solving other problems. This might be a further point of future work. But for today, let's summarize what we have seen. We have seen counterfactual explanations for violations of real-time properties that are very importantly based on this concept of Halpern and Pearl causality, on this formalism, and really on this counterfactual reasoning of Halpern and Pearl that can capture both actions and delays. We have seen no example where the combination is important, but I think you are aware of examples of real-time systems where the combination is important. The notion preserves decidability despite its infinite range by the automata theoretical view, and we have implemented for automated error localization so that in the end, our enterprise board computer can be managed to go to warp. And with this, I want to thank you.
Thanks, Felix. Any questions? Yes.
Hi, so my question was related to the motivation behind causality, right? So traditionally, like geographical causality is based on mostly like Bayesian networks and intervention of actual explanations and so to do combine with this and also like while choosing counterfactual and not talking about like calculus or something like that. So like setting.
Very good question. So I think what you are referring to is this probabilistic interpretation or this probabilistic view on causation. And I think what really helps is to look at this ladder of causation made up by Pearl, where he has on the very bottom this observational causality, which is just stochastically what we know with correlations. Then there is the mentioned interventional perspective, which is a probabilistic idea to get this do interventions, these do probabilities, and to work on a probabilistic setting. And then if you have concrete things, so it's not about probability at all. We do not talk about stochastics there. We don't talk about probabilistic systems, no probabilistic model checking or so. We have a concrete thing. So whether you or what you have done today, not what a whole population has done statistically, we then go in this area of counterfactuals, and there we are. It's just a third step of this ladder of causation. So we can really recommend to look and think about this ladder. And regarding your second question, I think as we have no probabilities here, if we have no probability distribution, we have no data that we measure, but we come from the formal method community. I think it was from the very beginning quite clear that we want to work with counterfactuals and not with interventional data.
So just one follow-up, like I think it boils down to using like causal diagrams in his, statement, like causal diagrams should be there. So would you argue that using timed automata is like a causal diagram or something?
Good question. We thought about embedding causal diagrams and causal graphs and the structure causal models into real-time systems and vice versa. I think there is something, but we have not found something there yet. So my feeling is you might have the possibility to do things, but not sure yet.
One final question.
Question is that here in this definition of probability, you have this condition that if it doesn't occur, then the error shouldn't occur in some sense, right? If we drop this condition and useful from a practical perspective.
So the question is whether it would help if we would drop.
Since we're okay with an explanation where you're saying that, okay, I mean, this event definitely caused this, but something else could have also caused this in some sense.
I'm not sure whether I'm getting the question correct, but I mean, as soon as you do model checking, and as soon as you know that there are non-violating runs, you somehow know that there is something there causing your violation. But the interesting question and what motivated us is to find those things that caused the violation. And
There could be faults which have multiple disjoint causes.
Correct.
very good question then. So this notion doesn't give you one explanation, but there might be multiple explanations. So in our example, that's too far back. In our example, also doing the energy at the second step might be or is a explanation, because if he doesn't break, if he doesn't do the energy but open the brake once again, you would remain in this intermediate state and not continue to the error state. So there might or there can be multiple causes in one setting here.
Nice. Thanks a lot. I think let's thank the speaker. But before that, I think we should ask him the opportunity to ask back questions.
Okay.
Any particular question?
And it should be hard or
Super hard.
super hard. Yeah, I mean, then what is the theorem Halpern can't found? So what is the theorem that Halpern cannot found, stating that this is the right definition? How can we state a theorem saying this is a right, this is a good causality definition?
Oh. No, here. Yeah.
If it satisfies the examples.
Good enough?
I give the brownie points, yes.
Okay. All right. Thanks a lot. Yeah. Thanks, everyone. That's been an excellent session.
Which version of the